Okay, thank you. I'm going to be describing primarily the lightning and atmospheric chemistry relationship that's being studied through the deep convective clouds and chemistry experiment. And I have a whole long list of contributors here that all helped put this talk together. So I'm not going to name all the names. It's just going to take too long. So anyway, let's move right along. Well, lightning is responsible for approximately 10 to 15% of the total NOx emissions globally. So this amounts to about 2 to 8 teragrams of nitrogen per year. But of course, you can see that range. It's a factor of 4. So we really need to try to narrow that range as much as possible. And that's, of course, one of the major objectives of the DC3 experiment. So now much of this uncertainty stems from really little knowledge of how much actual NOx is produced per flash or per unit of flash length. So now most of the lightning that is produced is injected in the middle and upper troposphere, where it has a relatively long lifetime compared with NOx in the boundary layer. So this NOx that results from lightning has a really strong importance for the production of ozone. Ozone in the upper troposphere is where it has its maximum importance as a greenhouse gas. Now, there's been a variety of methods that have been used for determining lightning NOx production, and there's been many theoretical estimates made. There's been lab experiments where you generate sparks in a controlled setting. There's been previous experiments where analysis has been conducted in detail of NOx observations from aircraft in comparison with the observed flash rates. We've run cloud-resolved chemistry models that have been constrained by observed flashes and aircraft observations. And then there's been also analysis of satellite NO2 data. So this just is a brief summary of some of the NOx production amounts per flash that appear in the literature. This is not by any means comprehensive, but it sort of gives you a flavor of what's out there. Some theoretical estimates were as high as 1,100 moles of NO per flash for cloud to ground, and basically 1/10 of that for intercloud flashes. Some laboratory work gave about 100. Some of the work that my group has done for mid-latitude storms has come up with an average of about 500 moles per flash. This is through use of combination of cloud models and aircraft data. And then also we've been employing satellite estimates based on NASA's OMI satellite, the ozone monitoring instrument, which also measures NO2. And we've come up with about 440 moles per flash based on those data. Then, however, Bill Koschak is combining LMA data with theoretical estimates and is getting over 400 moles per flash for cloud to ground, but much less for ICs. Aircraft data have been analyzed now in the tropics for several experiments that were conducted under European sponsorship, and there's been a range all the way from about 70 to 380 moles per flash there. We've done cloud resolve model estimates for a Hector thunderstorm in the islands offshore of Australia and come up with 500 moles there. Satellite observations in the tropics have been much less. So in general, tropical flashes have seemed to produce less NOx per flash than mid-latitude, and this has been hypothesized by some of the work by Heidi Hintrieser from DLR in Germany. And this may be related to possibility of longer flashes in the mid-latitudes compared with the tropics. And this needs a lot more work, of course, to really determine if this is the real reason. Now, the Deep Convective Clouds and Chemistry experiment was conducted during the latter half of May and during June of 2012. There were 3 study regions. The northeast Colorado area, a region stretching from central Oklahoma into West Texas, and then the northern Alabama region. And this just lists a couple of the major objectives of the DC3 experiment. and it was to characterize the convective transport of emissions. It was to study the storm dynamics and physics, to study lightning and the production of nitrogen oxides, and the effects of the hydrometeors on the chemistry. And then, of course, the production of NOx, of course, leads to the photochemistry that produces ozone. And we also wanted to look at what happens to the chemistry 12 to 48 hours downwind. So here, and of course, this talk is going to be focused on the lightning and its production of NOx. Let me start off with a discussion of what the ground facilities were that were important for this work. In northeast Colorado, we had two radars, the Colorado State Chill and Pawnee radars. These are important for getting polarimetric data. Also soundings that were conducted for the environment in that area. And then a lightning mapping array was set up, and we'll hear more about that in later talk in this session. So this is just pictures of the Chill and Pawnee radars and one of the LMA sites. And here's a little more detail on the LMA. There were 15 stations in northeast Colorado, and this is really probably the most sensitive and highest resolution LMA network that's been set up to date. This is just a picture showing the LMA coverage, which is this purple circle. And then within that here are the various dual Doppler combinations through use of the Chill Pawnee as well as the Denver and Cheyenne NexRad systems. So this is just one sample of a very short period of data from the 22nd of June case in northeast Colorado. Here the LMA VHF sources are demonstrated here for a very electrically active period of this storm. This shows them here in this function of east-west distance and north-south distance. Here is a function of altitude across this direction, and here is a function of altitude along in the y direction. So there was a very, very intense set of sources that were detected from about 6 to 12 kilometers in the storm. Now moving on to the Oklahoma and West Texas areas, this shows the LMA coverage stretching from central Oklahoma back into West Texas. Also, so this is really the combination of three networks here: one in central Oklahoma, one in southwestern Oklahoma, and one down here in the Texas Panhandle. And also in the Oklahoma region, there was good radar coverage that was provided by the Norman NexRad as well as the Oklahoma University radar. And then also, in the western part of this domain, we depended on the SMART-R mobile radars to give us good coverage. And this is one example of the storm that occurred from the evening of the 29th into the 30th of May. And here's just a nice photograph of that, as well as a radar depiction of a whole series of cells that were occurring in western Oklahoma. And here's the LMA depiction for that here with a really strong set of VHF sources showing up in this region here in the vertical, and here in this particular cell in especially. And then on the left is some of the sounding data that were taken. This is electric field measurements that were taken by balloon. In the northern Alabama network, we have three radars. These were the Armor and Max radars located at these locations, as well as a combination with the NexRad Huntsville radar that's located here. So there's various Doppler combinations that can be made with this. And then the green dots are the LMA network here in northern Alabama. And then there was also mobile sounding capability as well. And this is just some pictures of the two radars, the Huntsville Armor, located at the Huntsville Airport, and then the mobile MAX radar. Both of these dual polometric. This is a mobile version that's mounted on the back of a truck. And this is one example from the northern Alabama area, June 5th storm. This was a major system here in northern Alabama, and that here's where the LMA sources have been plotted over top of a radar depiction, and you can see that there was quite a bit of lightning activity out here in the leading stratiform area. And then if you want to look at more detailed work that's been done on some previous storm prior to the DC3 experiment, I think back in 2007, Larry Carey has a poster on Tuesday afternoon. Now, we have all these facilities I've described, and what we're interested in doing now is coming up with what exactly the products are going to be that are going to be useful for the DC3 analysis. And what we've decided is on these four types of products that will be produced on a 3-kilometer grid for each of the 3 study areas that I showed before. And this is just a raw VHF source count. And then we'll have a gridded data set for the flash origin, and then one for flash extent, and then one for flash area. And so these are the gridded type products that we anticipate. And this is an example from the Colorado network that was provided by Ron Thomas from Mexico Tech. This is a gridded 3-kilometer set of VHF sources for the June 22 case in northeast Colorado. And then this is gridded flash counts shown here on the right-hand side for the same storm. Now, what we also would like beyond sort of these standard products is some depiction of flash length. And this is going to be a fairly major effort that's going to come from each of the three major processing teams at each of the Alabama, New Mexico Tech, and Texas Tech. And generally, these are somewhat different algorithms, but I think Eric Bruning in the next talk is going to be discussing at least one of these. And so we're going to have sort of a comparison of what is obtained in terms of flash length in the DC3 study areas from each of these techniques. And of course, what we want is, of course, total length, as a function of time in each of the studied storms, and also we want altitude distributions of the channel segments. So this will be really helpful in the modeling of these systems. And also, these LMA data will be very useful in comparison with the dual polometric radars in terms of being able to come up with new and better ways of predicting, developing relationships that can be used in predicting flash rates. So now let me move on to some of the aircraft measurements that were made during an experiment. We had 3 aircraft, the NASA DC-8 aircraft, the NCAR G5, and the German DLR Falcon. And on the NASA DC-8, the NOx measurements were made by Tom Ryerson from NOAA Esrol. And this is a chemiluminescence instrument that measures NO, NO2, total reactive nitrogen, or NOY, and ozone. And what's going to be done is that Ilana Pollack from NOAA is going to be using these data to try to constrain lightning NOx production per flash. And she has started with case studies from the Oklahoma on these dates. And the idea here is to try to narrow the estimates of NOx production per flash from the rather wide range that exists in the literature now. And then on the NCAR G5 was measurements made by Andy Weinheimer. This is a two-channel instrument, one for measuring NO, one for NO2. And again, this is a measurement using the chemiluminescence technique. And this is just one sample of some data that he has plotted up. These are various aircraft passes in the downwind area of the anvil for the storm on May 29th in Oklahoma. And this was a major event that's being studied by several of the DC project team. And all these dots are flashes that were detected by the USPLN lightning network at various times. The older flashes are in black, sort of the mid-range is in orange, and then the newer ones are in pink. And you can see that here, right here, is where the maximum NOx measurements were made. Here, measurements were in the range of about 800 to 1,000 parts per trillion of NOx. And this seems to be right downwind of some of this major lightning activity that was occurring through this region right here. So then on the German Falcon, another chemiluminescence measurement was made there of NO. And also for ozone, and they are going to be computing NO2 through photostationary state calculation using those NO and ozone measurements. And then this is just a sample of some of their data for a major mesoscale convective system that was sampled by that aircraft over Missouri and Arkansas during the 11th of June. And you can see that in black on the on this plot right here is where NO mixing ratios reached about 5 parts per billion. So this was probably some really fresh NO that had been produced by some very frequent lightning flashes. And so this is the list of dates in which they're most interested in doing their studies. Now, of course, this was not over one of the LMA regions, so they're going to be relying on NLDN data, for example, for their studies. Now, post-mission, there's a variety of analyses that have been initiated, and one of them is a model study using WRF-Chem. This is at 15-kilometer resolution, so this is not at cloud resolving scales. This is using parameterized convection using the new Grell scheme. And this shows the various other characteristics of what went into that model. And the lightning NOx scheme is discussed here. Here, the flash rates were predicted using the cloud top height, but that was defined using the level of neutral buoyancy minus 2 kilometers. And this technique is described by a poster by John Wong, which is on display right now. And here we've put 500 moles of NO per flash and into the model. And this is work that Mary Barth has contributed here, and I believe that she has a poster on this as well. And the vertical distribution is been established by the modeling work that Leslie Ott had done back in 2010. But anyway, the plot on the right here shows the model prediction of NOx from this 2930 storm from Oklahoma. And here's a maximum here up in the range of, I think, 1 to 2 ppb. And then the aircraft data are plotted as these small circles here. And you can see that we're getting basically in the same range from the measurements, just that the model has the storm somewhat displaced a bit to the south. So all in all, I think it's a fairly good simulation. Now, we're also going to be doing cloud-resolved simulations with the WRF-Chem as well. And also, a NOx tracer was simulated using WRF in forecast mode during the experiment. And these were the prediction schemes for flash rates that were used in that in those predictions, and then also will be used in these post-mission cloud-resolved simulations using WRF-Chem. And these predictions of flash rate, this is total flash rate, and we've been using, adjusting that using, or dividing it up into intercloud and cloud-to-ground rates based on the Boccipio climatology. But these flash rates will have to be tested against the LMA flash counts that are going to be coming out of that work. Now, in this cloud resolve work, we've been putting the lightning into the model using Gaussian distributions for IC as a bimodal and a single mode for cloud to ground. And these lightning channels are set to maximize at about minus 15 C and minus 45 C. And however, of course, the LMA data will give us good information on each storm as to what the vertical distribution of the flash channel segments is, and we'll be able to improve on this algorithm for each of the storms that we simulate. So the way that we'll be able to deduce how much NOx is being produced on average by a given storm is that we'll compare the model and aircraft NOx mixing ratios at various altitudes in the cloud to determine whether our assumption, which probably will start with the 500 moles per flash, and see if that overestimates or underestimates the observed aircraft measurements, and then do adjustments to the IC and CG production rates as necessary to try to best match the observed aircraft measurements. Now, also, the improvements, as I mentioned, can be used to, the LMA data can be used to help us improve the flash rate schemes, help us determine whether some of these schemes are best for certain regions or certain storm types, and help us with the vertical distributions, as I just mentioned. We can also use the LMA data to help us determine where within the storm the lightning NOx should be placed. It'll give us a better idea of the intercloud to cloud to ground ratio, and also give us that flash length information, which we can use also. Now, these are three of the storms that we'd like to simulate. The 29 May, of course, is already, Mary Barth's simulation is already underway with the parameterized convection, but we'd like to also do this cloud resolve mode, and then also do one for Alabama, and also do one for Colorado. And this is just for starters, where there's plenty more cases out there as well. So now the last part of the talk will be on some estimates of NOx production during DC3 that have come from some satellite observations. This is the NASA's OMI instrument on NASA's Aura satellite, which passes over over an area at about 1:30 in the afternoon. This is a polar orbiting satellite measuring NO2. And what we do here is these are representative of the column amounts of NO2 in the atmosphere, and so what we're trying to do is get an estimate of the lightning contribution to the column. So basically, what we need to do is subtract off the stratospheric component and subtract off a pollution component. So I can't take time to go into all the details of this, but that's basically what we're doing. And then we also want to convert the lightning NO2 to lightning NOx. And here we use the upper tropospheric NOx to NO2 ratios from the DC-8 and the G5 observations by aircraft. And then also there's some NO2 loss, of course, during transport, and we have to take this into account, and we're using an assumed lifetime of 4 days along back trajectories. So this is one case from June 11. This is where there was a very active mesoscale convective system going on over Illinois and Missouri. And based on the satellite observations, we get 11.9 megamoles of lightning NOx within this red box. And the transport times were fairly short in this case. Here's our back trajectories, and these go back to the lightning that was occurring right here over Illinois and Missouri, and the mean transport time was only about 4 to 5 hours. And we counted up this is based on NLDN flashes at this point, since we don't have the LMA flash counts yet. And so we have over 165,000 flashes, and we take those number of moles that we get from the satellite, and we're getting about 72 moles per flash in this case. Now, this is a case where it was on the 30th of May, this was downwind from that 29th case over Oklahoma that I showed previously. And here within this box over western Tennessee, eastern Tennessee, western North Carolina, and southwestern Virginia, we're getting about 14 megamoles of lightning Knox within this box. And here, the transport along the back trajectories takes about 16 hours to get back to the lightning over Oklahoma. So here's our lightning showing up in the MLDN data over Oklahoma. So also some small contribution from some lightning over Mississippi. And here, when you divide out, we get about 92 moles of lightning Knox per flash. And then using the aircraft data from the DC-8 and the G5, what we did was average those aircraft data into 1 hectopascal intervals in the vertical. Wherever there was an aircraft measurement here, we have an X. And these are preliminary data at this point. But anyway, if you vertically integrate all these measurements here from about 400 millibars up to about 200, you get about 1.4 times 10 to the 15th molecules per cubic centimeter. And whereas in this region as a whole, the OMI measurements were about 1.18. So you can see that the satellite is giving us a little bit of an underestimate by about 16%. So it's really not too bad. But anyway, if we adjust upward our moles per flash that we had calculated from 72, that if you take the 16% low bias into account, that pushes it up to 84. The 92 goes up to 107. Anyway, but this area here in the Western Carolinas and so on was very heavily influenced by the lightning from Oklahoma on that previous day, and about 36 to 47% of the column amount of NO2 in this region was from that lightning back in Oklahoma. So now, to summarize, the DC-3 experiment has really provided us a really excellent set of data in 3 regions of the country, and this is all aimed at being able to give us better estimates of NOx production per flash. And so between using the lightning mapping arrays and the radars and the aircraft chemical observations in the storm inflow and outflow, we should be able to narrow the range of lightning NOx production that's out there in the literature now. And so the LMA data, of course, is going to be very vital to that, and some of the initial products are going to be archived very soon. That's the flash count and flash extent. And then ultimately, the flash channel lengths and the vertical distributions will be available, and this will be really helpful in the modeling aspect of the project. So the analysis is just getting underway, and some of the aircraft data are being analyzed, some WRF-Chem modeling is ongoing, and some satellite-based observations are also going on. And these values that I obtained of around 100 moles per flash are somewhat lower than what some of the other estimates over in North America have been, but they're certainly well within the range of literature values. Thank you.
We have time for perhaps a question. Steve.
Hi, Steve.
Yeah.
Or maybe future work, are you able to evaluate the impact for planetary non-nuclear ozone from the lightning, its contribution to revenue cause exceedances and other things?
Well, certainly, if we get a good representation of the lightning NOx in the models, whether they be regional models or global models, certainly they can give us good estimates of what the contribution of lightning is to surface ozone and how much to upper tropospheric ozone. Surface ozone, of course, for air quality purposes, upper tropospheric for climate aspects, because that's where ozone maximizes its effectiveness as a greenhouse gas.
We'll ask any further questions out in the hallway after we're going to move on to the next talk now. So let's thank our speaker again. Our next talk will be Fractal-based lightning channel length estimation by Eric Bruning.
Next slide. Yeah, probably. Yeah. Plenty of cord there. We advanced.
All right.
All right, I'd like to acknowledge Ron Thomas, who provided a number of figures and some nice analysis for the initial portion of this analysis that pertains heavily to the DC3 objectives that Ken Pickering just discussed. I've also had a number of conversations with colleagues from Alabama and NASA in sort of getting oriented to all the different things the community is doing and trying to estimate channel length. So this talk focuses specifically on trying to estimate the knocks per flash and per unit channel length, and especially focused on, in the end here, trying to get at this vertical distribution of channel length. And there's some challenges associated with that. The channel, as has been discussed in the literature for a couple decades now probably, the channel itself is a fractal object. And in the most sort of pure form of that means that the channel would then have an infinite length. That obviously causes us some problems. And we also have some variability in the LMA detection with range and with individual networks and their noise floor, as well as the number of stations those networks have. And so maybe flashes look differently in these different networks. So what this talk is about is exploiting this fractal geometric character of the flash to assess these length estimates and see if we can maybe understand this problem a little bit better or in a different way. All right, so this is a single flash from Colorado, from the Colorado LMA during April, I believe. And this is a very, very well-resolved flash. And Ron Thomas did some work to connect the dots and actually put together the branched network. And then from that, you can calculate the total channel length. And so there's white channels that are basically this main channel segment, as well as some little green channel segments and little red dots that are sort of leaves on the end of all the branches. And if you add up all the length from the white segments, you get 260 kilometers, and you can double that by adding the green segments. So which one of those is the right length, and which portion of that length is relevant to the Knox chemistry? And given that the LMA is not necessarily detecting all of the structure in the channel, even though it's got quite a lot of it, is there even more detail that we're missing, and the right length is maybe 1,000 kilometers? All right. Well, another method that we can use to estimate the channel length is this box covering method, and look at how many boxes are needed to cover the flash. So if we assume some characteristic channel stepping length that we use as our box size, and we multiply by the number of boxes it takes of that size to cover the flash, you can calculate a length from that. The LNOM algorithm that Koschak and Peterson at Marshall are developing uses a similar idea to this. We'll show it here for this Colorado data as well, and this is one of the things we'll be comparing going forward, as was mentioned in the last talk. We have to choose a box size, of course, in order to do this, and there's maybe some physical assumption in there, as well as maybe something about the way the network works. This box size would obviously be far too large, and so we cover the flash with 8 of these giant boxes. We could go down to a smaller box size, and you start to actually pick up some of the branched structure of the channel when you do that, and you could imagine continuing this process iteratively down to a smaller sort of minimal box size of your choice. And this method of actually calculating the flash length is related to a sort of classical method for estimating the fractal dimension of an object, where a power law relationship and the number of box sizes that it takes to cover the object at a certain size forms a power law relationship. All right, so this is actually the result of choosing a bunch of varying that box size and looking at the estimated length. So this curve here, which follows a 3/2 power law for boxes larger than 700 meters, represents the total number of boxes, and that falls away from that power law and limits on the total number of LMA sources as it must. Then there's also this curve here, which is the total length calculated using that simple formula, number of boxes times the box size. And there's a peak in that distribution right around 250 kilometers total length for a 250 meter box size. Okay, so that peak in that distribution there is then close to the connect the dots length for at least the main channel segments, those white segments. All right, so the next step is we'll continue down this line of using the fractal property, and we'll look at flash length estimates using the flash area. So we'll use the fractal dimension of the object, the way that the curve fills space, and some of these box counting principles to come up with a length estimate. So we'll take a flash spanning area as what determines our largest box size. There's a length scale, the square root of the area associated with that. For our area measure, we'll take the area of the convex hull, which is the minimum area that covers the whole flash without having to make concavity decisions. We'll pick some channel step length that's our smallest box size, and we'll count the number of boxes at that size, and you can then derive this formula that is the square root of the area, so the length scale determined from the covering area to the fractal dimension divided by the box size times the dimension minus 1. All right, so what length estimate do we get for a variety of values of D and box size? I'll show you that in a second. First, what values of D should we use? There's a number in the literature. There's 4/3, 1.5, 5/3, and 1.7. I'm going to look at the bottom three. The top one was determined from two-dimensional flashes, and we know we have two-dimensional pictures of flashes, and we know we have a three-dimensional object. So we want to use at least 1.5, which is what Senuto et al. Argued. This is a power law relationship, so as you would expect, there's a very high sensitivity to your value of D and the box size. Intriguingly, at that 250 meter box size, which is the top row in the table, if you look at that entry in the top row, or maybe 300 meters, that's, again, was the peak in our box covering length estimate. The fractal method using a dimension of 1.67 or 1.7 is in the ballpark of that 250 kilometer channel length for that box size. We could also do this with the three-dimensional volume. We're not restricted to area, so we'll just use the cube root of the convex hull volume. Again, it's a power law relationship still. But again, at 250 or 300 meter box size and some of the larger values of dimension, you can get a ballpark estimate that matches the other estimation approaches. Of course, you could use a smaller fractal dimension, and then you just have to use a smaller box size to get the value that you might try and target. So for both 2D and 3D, there's a range of estimates, and those range of estimates for some plausible box sizes are comparable to the connect the dots variability. And so we're still left with this question: what's the right dimension, and does the box size have physical significance? And I think it's interesting to try and work towards determining those, because those are probably fundamental to the character of how the flash is developing and physically significant. I'm going to do some further work now. I'm going to adopt these two values for those further experiments, 5/3 and 250 meter box size. We could pick a different one, and it's actually doesn't matter for what I'm going to do next. All right. Okay, so to try and partition the total length by height, how are we going to do that? The algorithm that's used to calculate the convex hull is actually, as part of that, you calculate a Delaunay triangulation of the original point sources. So this is a natural neighbor connectivity. Given a length estimate, what we'll do is we'll use the subvolumes that are tetrahedra produced by that triangulation to take into account the geometric character of the flash, and also use that as our minimum box size. And we'll weight the weight the total length estimated from the fractal method by using the fractional volume of these little subvolumes formed by little tetrahedra of source points. All right, so there's the equations to do that, and the length estimate is in the end given by the lower right-hand equation, and it has a nice symmetry with our other method. These individual subvolumes act as our local box size, and then there's this global hull volume that we'll use. All right, and if you actually run that through a real flash, you produce a vertical length partitioning that actually happens to be nearly identical to the VHF source histogram. The length estimate is the red curve here. There's some differences because we're using a slightly different method, but the source altitude distribution and the vertical length distribution actually follow almost exactly the same curve, which is sort of remarkable. All right. So to summarize what we've done here, we've developed this sort of two-step approach that takes into account the intrinsic geometry of the flash. We assume some properties of the flash that the dimension, this minimum box size, and the hull volume. And that's mostly independent of the detection efficiency of any individual network. We just need an accurate volume of the flash, and the networks generally are pretty good at getting that right, even for the less sensitive networks. And then, in order to calculate the local flash length, which we use for a vertical distribution, we weight that total length that we estimate globally by the local natural neighbor volume mapped out by the individual sources. If you do the tuning of the dimension and the box size, you can get comparable length estimates from the various methods, but it's very important to be aware, of course, that those errors are highly nonlinear with the changes in the global parameters, and that's what we'd expect with a fractal object. In future work I'd like to pursue here is to look at whether that global and local geometric properties, whether those relate to the distribution of electrostatic potential in some way. Can we infer that from the way the flash maps out space? And we could also do four-dimensional subvolumes and maybe play around with the time coordinate some and be completely unable to visualize what we're doing. But anyway, that's planned for the future, and with that, I'll happy to take questions.
To what extent is that sort of characteristic box size of 250 meters dependent on, say, the resolution of the LMA? If you had, say, a flash that occurred outside the LMA network versus one that inside, would you get a bigger box size outside?
Yeah, I haven't tested that, and I would expect that your intuition is right there, is that it's some combination of the actual intrinsic character of the flash and convolved maybe with the network. So maybe my statement isn't 100% accurate there, and that does need to be looked at. You're right. Right. Yeah, and I've left aside the entire physical question of which portion of the flash is making the channel that leads to the NOx, and obviously we won't probably with the current tools be able to resolve those tiniest scales, but there is some body of literature that looks at objects that are fractal as well across at least a portion of their portion of the range of scales, and so that's sort of the idea that we're drawing on here.
Okay, we're going to go ahead and move on. Thank our speaker again. Our next talk will be Lightning and Forest Fire Smoke Plumes by Tim Lang.
Mouse here. Okay, so this work is being led at Colorado State, but it's a collaboration between CIRA and New Mexico Tech and Colorado State, and I just moved to NASA Marshall, and so Marshall is probably going to get involved in this too. So what happened during the very severe forest fire season in Colorado in 2012 was occasionally above these major fires, you would get deep plumes, vertically deep plumes, and they would electrify. And it didn't appear to be a classic grapple-based thunderstorm electrification mechanism. So I'll show 3 examples. One is the Hewlett Gulch fire. This is the first major fire in northern Colorado. It burned a small area northwest of Fort Collins. It was kind of a boring day during the DC-3 project, so we decided to just scan the plume. And of course, smoke plumes show up pretty well on radar. You generally get this signature of modest reflectivities in the 20s, generally with correlation coefficient, which is with a polarimetric radar, the relationship between the H and V polarizations and the correlation between them. It's fairly low, and then the differential reflectivity tends to be fairly high. So you have kind of large oblate-looking type particles. And so this is actually, as it turned out, we were doing RHI scanning through this plume, and it electrified as we were scanning it. So it was a very fortuitous observation. And one of the neat things I want to point out here is that there does appear to be some slight lowering of ZDR aloft, which may indicate perhaps some icing or development of ice up there, and the correlation coefficient is also increasing, again suggesting possibly greater influence of meteorological scatterers. So what we see here is a plan animation of a composite view of reflectivity, differential reflectivity, and vertical velocity. And you get basically a blow-up of modest reflectivities in the 20s, and the lightning, as shown as LMA sources here, follows right thereafter. The plume here, again, you see is mostly very high differential reflectivity, indicating a lot of smoke and ash. And so we were also doing dual Doppler scanning, and this is really unique in smoke plumes. And what we see is a real burst of vertical velocity here, and then the plume is just downwind of that shortly thereafter. Now we project things vertically, going from south to north. You see development. This is a 10-kilometer MSL line over about minus 40 degrees Celsius. You see development of the plume above that line, and that's when you get the lightning sources, and they're all very high altitude. The differential reflectivity is a little bit reduced up there. It's going off the scale. It's below 1 dB. And then the vertical velocity here, you get development of the vertical velocity, and then the lightning occurs shortly thereafter. So we're able to look at this from the satellite perspective, and we actually had a fortuitous MPP VIIRS overpass shortly before the plume electrified. And this is a true color image, and it has been enhanced to show the smoke plume, which is this sort of brownish area. It may not show up very well, but it's a little bit brownish there. And then we've got short wave and long wave IR. If you look at where the lightning is occurring, it's in the long wave. This is it's sort of out of the deepest cold cloud area. And what's interesting is if you see a development of a hot spot here, boom, and that's when the lightning occurs. So these hot spots are visible to GOES shortwave IR, and so they indicate, they're used to locate fires. So you get that hot spot show up, the lightning occurs, and so that's kind of an interesting result. The lightning itself is fairly compact vertically. This is source density, and then this is an individual flash. You see the sources are sort of located over about a 2-kilometer depth with positive charge above and negative charge below, apparently. There's a lot of precursor activity, so it's kind of pop, 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 boom, pop, 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 boom is how things are happening in these flashes. So it's all indicating fairly weak electrification process, at least what it appears, because the flashes are pretty small, they're vertically compact, and there's a lot of precursor activity, so it's hard to get them going. Okay, so now the second example is High Park Fire. This is a fire that burned closer. It basically burned all the area that the Hewlett Gulch Fire didn't burn in Larimer County. And this is a picture I took from my office window, so I had a great view of it early on in its lifetime when it burned down towards Horsetooth Lake. And of course, the one day we didn't scan the plume was when it electrified. But given our previous experience with the Hewlett plume, we did get a lot of null cases scanning both RHI and dual Doppler of non-electrification plumes. So what I have here is just an XRAD composite. And it's a little hard to see in here, but this is where the fire is, and then you've got these little bursts of plume that come off, and you see little bits of black dots, and that's the occasional electrification of the plume. Again, vertically, you get that deep development above 10 kilometers MSL, and that's when you actually get the lightning there, and there's some lightning there, and then it just kind of drifts downwind. This is going from west to east. So here I'm not animating the shortwave IR, instead of animating the GOES visible imagery. You see really rapid development of the plume through the period that it electrified. The flashes kind of occurred over a period of about 1 to 2 hours. And then this is a shortwave IR showing a little bit of cold cloud. Long-wave IR also showing just a little bit of cold cloud, kind of in the 240 or so Kelvin. And the lightning is occurring in that. So this is a little different than the Hewlett case. The lightning occurred in cold cloud, or obvious cold cloud. When we scanned the plume on other days when it didn't electrify, of course it was shorter then. And so I show the same thing here, modest reflectivities, fairly weak correlation coefficient, very strong differential reflectivity. I'm kind of off the scale here, which terminates around 6 dB. So very, very, very large oblate looking particles, and these are kind of classic smoke plume signatures from polarimetric radar. So the plume looks about the same as it did for the Hewlett Gulch, and also likely, the plume kind of looked like this, but we don't have evidence of what it looked like when it was very vertically developed and electrified, what the polarimetric variables were. The lightning, again, was fairly similar to, it was very compact vertically, with one exception. Again, some precursor activity, and this late flash is interesting because it did show a little bit deeper charge layer. But for the most part, things are kind of clustered with positive charge roughly above 10 kilometers and negative charge just below. Finally, the Waldo Canyon fire. This produced some really dramatic images and was very devastating to Colorado Springs. It burned an entire subdivision and caused a very large portion of the city to be evacuated, including the U.S. Air Force Academy. And during the day, this all occurred during a day of rapid development, a few days after the fire started. And during that time period, when Colorado Springs was being evacuated and when this subdivision burned, right before that is when the plume electrified. Showing the Plan view, of course, this is too far away for chill to scan, so this is, again, just an XRAD. I'm going to call a few things here to your attention. Of course, there's a lot of just random convection over the mountains here, including this storm, which was electrified. This is a very typical, kind of typical looking thunderstorm. But down here is where the plume was, and you see it develop. And there's some lightning there, some lightning there, lightning there. And then what's interesting is you see a flash that comes from the northern convection down into the plume smoke itself. So there's possibly some interaction there. And there's also this fine line that comes out during the development of the plume. The vertical development here, again, gets above 10 kilometers, well above it, but modest reflectivities, 10s, 20s, and that's where the lightning occurs. And this is that stuff to the north, a very typical looking thunderstorm, develops, falls out, nothing special, but there is a little bit of a hint of that flash that goes back into the plume itself. Again, there's much like the Hewlett Gulch fire, there's a really nice looking hot spot here, and the plume lightning is all downwind of that. And then the actual convection is north of it, and that's where some of the cold cloud is. But down where the plume is not where obvious cold cloud is. So we're a little bit further outside the network, so things aren't as tightly clustered, but given the error considerations, I would say that this is roughly the same thing we've been seeing before. Basically, positive charge above 10 kilometers, negative charge below, fairly small, compact flashes. Later on, I show points, and this is that northern convection. Oops. This is that northern convection. This is the last bit of the plume lightning, which again occurred over about a 1 to 2 hour period, very intermittent. And this is that flash that kind of connects them to. And you see it goes out on what appears to be an upper level positive charge layer out towards the plume. So conclusions. The smoke plumes above the forest fires electrified when they grew to high altitudes during favorable meteorology. I didn't show them, but you saw in the soundings, they're very deep, dry adiabatic layers, and generally explosive fire growth, especially during the Waldo Canyon plume. That was probably the most dramatic example of that. The flashes tend to be vertically compact, intercloud flashes, small in area, with some precursor activity. When we had dual Doppler information, it showed significant updrafts, several meters per second, and that's probably an underestimate, and growth above 10 kilometers MSL before things electrified. And we often saw coincident hotspots in the shortwave IR, although one case showed intervening colder cloud. The polarimetric observations do not support the inference of Groppel in these storms. The reflectivities are too low, the differential reflectivities are too high. But although there is that hint of potential icing occurring above in the high altitudes of the thunderstorm. So perhaps this is maybe due to some weak electrification with ice crystals starting to form or rimed ash particles. I'm not sure. Forest fires are known to throw out a lot of ions and throw up a lot of nucleotides. Perhaps there's some sort of ionization going on up there. And also, perhaps the reduced break-even field at high altitude is going to be important. One thing I want to point out, though, is even though this is a novel observation, it's not necessarily a novelty. These things occur during rapid development of the forest fire, and so you might be able to use this to get information about forest fire state and location. Thank you.
Time for perhaps a quick question.
Do you know the polarity, or are you guessing?
Based on the development of the flashes, it appears to be positive charge aloft and negative charge below, so kind of a normal polarity IC discharge in the high altitudes.
Let's thank our speaker again.
Thank you.
Our next talk is an invited talk, Lightning Mapping Observations during DC3 by Paul Crable.
Okay, so the title of this talk is Lightning Mapping Observations during DC3 in Northern Colorado, by myself, Bill Rasan, and Ron Thomas from our group. And I acknowledge we've been working with Colorado State University people, Tim Lang, and graduate students, and Steve Rutledge. Okay, so this is just a quick initial review of the Colorado LMA. Consisted of 15 stations, as Ken Pickering mentioned, spread over about a 100 kilometer diameter area. So it had a very good reach out over into the three-state area, parts of the three-state area, northern Colorado. Let's see. Unfortunately, this is an Apple presentation, and the pointer doesn't show on this. So what I'm going to do is just back out of this. And okay, now the pointer will work. Okay, so the network is basically in Weld County and covers up into Nebraska here, Wyoming, and a reasonable amount of Colorado. Okay, do that. Yeah, that's all right. We'll just leave it this way. Okay, so this is what an individual station looks like. It's a completely standalone. It has, let's see, so what I'm going to do is get out of this. Do it this way. Okay. All right. And let me just go over here and click on one of these pictures here. All right. Okay, now. Okay, so they operate off of solar power and have cell phone data modem links into the internet, and so there's no connection required. It's completely standalone and autonomous and records automatically. And the data are communicated back in real time to a central processing computer in New Mexico for the real-time data analysis. Let's see, so we'll do it this way now. Okay. All right, so the network was very sensitive because we're able to put the stations in remote locations and where there's not much background VHF radiation. And on the left panel here, you can see the straight lines of airplane tracks flying through cirrus clouds, which we routinely pick up with this network. On the right-hand side is an example of some real-time data. Both of these are real-time data from a north-south line of convection that was moving in from the west on June 2nd, which was sort of early stages of DC3. So these are our real-time displays. Okay, just summarize the results so far before we get into actually showing them. Basically, we obtained excellent data in collaboration with Colorado State and the Chill radar. The data analysis is very much a work in progress. In this presentation, I'll just show some brief examples of the kind of observations we obtained during DC3. One of the interesting things about this particular area is that there's a wide variety of storm types and electrical structures there, from small isolated systems, storms, to bigger systems, supercells, et cetera. So and the electrical properties of these storms were ranged all the way from normal to various types of anomalous polarity electrification. And the anomalous storms were very common. And basically, it characterized the storms as in this area as when, at least if they're anomalous, that they're characterized by a deficit of cloud grounds, both negative and positive, or tend to be relatively infrequent compared to the amount of intercloud lightning. And, of course, a detailed study of this, which we're just getting started on, should be very interesting and very useful in understanding electrification processes. Okay, so the first example I'll show is of the same flash that Ken Pickering talked about, where Ron Thomas has done an analysis of the channel length. And this occurred early on, right after we got the network set up. And the panel on the left shows two flashes during a couple minute time interval. The one we're going to concentrate on is this one here. And it was located right directly over the chill radar site, which is that little green square right there. And if we zoom in on that, we can see that it's a bi-level intercloud flash. A bi-level intercloud flash between, and it's upside down. It's it's the opposite of normal polarity, namely inverted, and it's between an upper level negative charge and a lower mid-level positive charge, indicated. And so the blue sources up here indicate this is what we call charge identification. It indicates where positive breakdown was propagating into negative charge regions at high altitudes, and the red sources indicate where negative breakdown is propagating into positive charge. Okay, so we zoom in on this, and I'm going to show an animation now of this flash. I can't really read okay, I can read it over here. So as I described what the two colors correspond to, basically the red is positive charge regions and the blue is negative charge regions. And so if you look down in this part here, in the plan view, you can see that there's some differences, significant differences between the blue sources and the red sources. Namely, there's differences between positive breakdown and negative breakdown. We'll see a little bit more about that later. Let's just go on to the next one at this point. So the next one is the animation. And, yeah. So now I want to go into this mode. How do we get in? Oh, hit play. Oh, okay, right. That, okay. Good, okay. Sorry, I was trying the wrong one. Okay, so, all right, so this is animation of the flash. And we'll go back through it again here. At this particular point, which is close to the end of the flash, you can see that the positive breakdown channels are extending uniformly sort of across this front with RF sources. And if we come back down here now and finish playing it, we'll see various K changes occurring between the upper and lower levels as it extends all the way out. I'll go through it once again. Notice that as opposed to the positive breakdown, it tends to extend continuously along all fronts. The negative breakdown is different. It does one main branch at a time. This is the first branch. Then we get a second branch. And if you look up here, now we're starting to see for the first time the VHF sources from the positive breakdown, which could be due to the retrograde negative breakdown, the so-called recoil type activity, but it could also is partially due to radiation from the positive breakdown itself, stepping of that. So if we just keep moving through, there's a little space between where the flash started, which is here, and where we start to see these sources, and that's because almost certainly because the radiation from the negative breakdown is much stronger. So if we can just step through here. Okay, and you can, as you watch this, you can see K changes come from upper to lower level. So we'll just leave it at that. Okay. All right. So get out right now. Escape. Okay. So what we can do to illustrate the differences between the positive breakdown and the negative is just stratify it according to altitude, which gives us, so on the left here we have the negative breakdown into positive charge regions. On the right we have just the channels that are associated with positive breakdown into negative charges. You can see already the difference here between the two a little bit more clearly. If we go to the next slide. Whoops. Looks like I've got to do that back over here, don't I? Juggling all these keys. let's just do it this way. Command Option P, right? Yeah. Okay. So this is Ron Thomas's analysis of the flash length, which Eric showed, and this sort of shows how the positive breakdown is very filamentary, finely structured, not a lot of tortuosity, not a lot of side branches, whereas the on the right and on the left, the negative breakdown is much more noisy due to side branches. Okay, I'm just going to digress here and show some results which will also be shown in a poster session this afternoon by Manabo Akito and Mike Stock on microsecond observations of the same kind of flash, namely a bi-level intercloud flash, in this case of normal polarity. And so this flash this data is obtained with a broadband interferometer operated in a Lamier laboratory. On the left is the LMA observations of the flash, and on the right are the interferometer observations of the same flash. And the LMA observations are three-dimensional, the interferometer observations are two-dimensional, and what Mike has done is to combine the interferometer data with the 3D LMA data to make what we call a quasi-3D version of the interferometer data. The interferometer data located 80,000 sources about for this flash, and as opposed to about 1,200 sources for the LMA. So it's substantially more more events. And it has much better time resolution. It's recorded continuously during the flash, and with on the order of 1 microsecond time resolution. So the next view graph here will show the animation of those sources. Let's see, I can't see the pointer. There it is. Okay. Okay, let me stop at about here. Okay. All right, so this panel up here shows the bi-level structure of the flash. Okay, you got this case of normal polarity. So this is negative charge here, and up above that is positive charge. And we're seeing continuous breakdown in the whoops. Let's see. Can go back up here. Oops. Okay. Yep, I managed to reset that. I'll just let it run this time. It's too dangerous to stop it. Okay, now we're starting to see the bi-level structure. We see a lot of red sources. That's recoil type breakdown in the negative charge region, or from positive leaders themselves. And then we also see the negative breakdown in the upper levels as well. And pretty soon here we'll start seeing K changes, which go all the way from the lower level all the way to either toward the upper channel or all the way up the upper channel into the upper levels. The point that I want to make here too is the following, that just estimating the channel length is not going to give you the whole picture, because what's happening is you've got multiple excitations of channel segments all over the place. And so estimates based on just channel length for NOx production, for example, are going to have to take it, or essentially have to take into account the fact that you get these multiple breakdown events, each one which are impulsive and would freeze in things like NOx. There's a K change at the end. So that's one of the, there's also very interesting implications of that in flash development. Okay, see where I'm at here. Okay, now going to electrical charge structure in the storms. Let's see. So these studies are aimed at elucidating electrification processes. We're just getting started on this aspect of the studies. For now, I've just been focusing on initial lightning sequences, and also in comparing the lighting mapping observations with the dual polarization chill radar data. Okay. Let's see. So here's an example of two small storms, the FAMA storm over Walt Lyons Place near Fort Collins, and then the lower circle is a small storm over Fort Collins Levelland Airport. And these two storms were both produced low lighting rates and they were normally electrified. The interesting thing about them is that here are well, this is the lightning in the FMA storm, the one to the north, and it produced 9 lightning flashes in about 20 minutes, over about a 20-minute time period. And on the right is the electrical charge structure of those discharges, showing that basically it's normally electrified. There's a mid-level negative charge, upper positive, and lower positive. And this normally electrified type scenario readily produced cloud ground discharges, negative polarity cloud ground discharges. In fact, both this and the next and the other storm, these are the two storms with the lightning inferred charge structure. And both storms actually began with negative cloud grounds and produced several within that first time interval. By contrast, here's what I call a Hereford storm, occurred on June 2nd of 2012. It occurred 1.5 hours later, so it's the same day as the previous one. It's just that the system was moving from west to east, and so the storms were moving with it. And we're going to focus in on the, and now let me go back to the escape out of this mode. Well, let's see it. Won't be able to change, so let's just leave it. Okay, so the Hereford storm is right at the triple point between Wyoming, Nebraska, and Colorado in the red circle. I've lost a pointer. And then the right-hand side just shows that same storm zoomed in. Okay, this is a full lifetime of the storm. The upper panel is I'm looking at the wrong thing. Okay, so the upper panel shows basically about 1 hour of. The storm lasted about 45 minutes. Okay, and during that time, if you look at the upper right panel, there were no cloud ground discharges produced for the first 34 minutes of that 45-minute duration. So obviously this was somehow anomalously electrified because if it had been normally electrified, it would produce many clouded grounds. And then at the end of it, it started producing clouded grounds, but they were all negative. And this just shows what the lightning looked like at the very beginning of the storm, the initial lightning activity, which is going to be most indicative of the possibly of the charging mechanism. And on the right-hand side, you can see that there were discharges occurring between mid-level negative and lower positive, and the mid-level negative and upper positive by those white arrows and white pluses and minuses. And so overall, this storm actually had a tripolar charge structure, three charge regions. It's consisted of really a double dipole. The dipole, that's what the tripolar structure consists of, is a double dipole, which in this case the negative charge regions overlap in the middle. Okay, this shows how the lightning activity during the initial stages compared to the vertical scan of the radar from chill. Basically what was happening, it looks like here, is that there's a strong updraft in the upper left panel, which is causing an overhanging echo, and the lightning is occurring in multiple dipolar charge regions in a higher reflectivity region. This shows an image. Well, let's go back to here. This shows the same thing, except exactly coincident with the radar, the time of the radar scan. And again, the upper panel shows a very good correlation between where the lightning was occurring and the higher reflectivity regions. The lower center panel shows an individual flash, which essentially discharged the lower dipole, mid-level negative and lower positive. And this is another flash which did exactly the same thing, just a little bit later. the point is, the question is why did, let me go back here. The question is why did this storm not produce, since it was essentially had a normal type electrification structure, why did it not produce clouded grounds? And the answer is that the lower positive charge or the lower dipole was much stronger. We can infer from that the lower dipole is much stronger than the upper dipole. And so there was enough lower positive charge to just prevent it from going on down the ground. Okay. Okay, the final storm we'll look at here is, or the final day is June 22nd, which is the day of one of the DC-3 airplane flights. And there were these are large supercell type storms that formed in quick succession, 3 of them off the eastern edge of the network. And in the top panels, you can see the initial 1 hour basically of activity in both the storms from the beginning lightning up to the state at an hour later with strong convective surges, etc. By the way, there's an airplane track there on the upper left. Okay, and so it's going to be challenging to, well, the point to make here is that the first cell, which is shown on the left, it had no lightning to start with, and then it started producing positive clouded grounds. The second storm, which was to the north up over the Wyoming border on the right-hand side, produced no lightning for about the first 20 to 30 minutes or so, and then produced a mixture of positives and negatives. Well, actually, negatives and positives. In other words, it started off producing negatives before positives. So the question is what was different from these, and just take a detailed analysis to go through. It'll be interesting to find out if we can sort that out, why those two were slightly different. And then this shows a chart structure in that system. This now is not the same as the previous storm. It's got a 3-charge structure, but it's an inverted type structure. Namely, it's got negative charge. It's got essentially a positive dominant charge in the middle, the orange sources, if you look, say, on the left-hand side, the vertical cross section, and it's with negative charge above it and negative charge below it. And that's at the very beginning of the storm, and then on the right-hand side is about 10 minutes in, 10 minutes later, showing that basically that the lower dipole was active. And the interesting thing here is that the right-hand plot it basically looks like an intercloud flash, and I can show that right here. Okay. So the right-hand panel on this one is that same flash, or flash which occurred in that charge structure, namely is between lower negative and mid-level positive, and normally that flash would just be between those two charges, and that would be it. But what happened is it produced a positive clouded ground discharge, and that's indicated by the rectangular square brackets in the top right panel, and. So what that's telling us is that the way this storm was different is that the positive charge region in the storm was very strong because it overpowered whatever negative charge was below it and produced an energetic 39 kiloamp positive clouded ground. Another discharge occurred shortly after that, which produced 56 kiloamp peak current. And then these just simply show radar overlays of that and of lightning sequences at various times during the early stages of the storm. And basically what this illustrates, if you look at the two bottom plots, is that the structure, at least downwind of this, was that of a inverted, what can be called an inverted tripole, namely positive charge sandwiched between upper negative and lower negative, and with the positive charge being dominant. Okay, and just in closing, just call attention to this upcoming paper. It's in press by Bruning et al., where he. So the question is how you can explain negative charges being at different altitudes in the storms, and he's come up with a very nice visualization of the concepts of how the transition occurs between positive charging of grapple, which is to the left of the dots in the curve, and negative charging of grapple, which is to the right. And it's a very nice result, which leads to testable hypotheses on whether the non-inductive ice rhyming mechanism or ice-ice collision mechanism can explain the continuous distribution of electrification scenarios. Okay, so summarize, obviously, just leave it at that. Thank you.
Questions? I'll try to see you guys.
Yeah, I can't see anything.
Yeah, I really can't see anything.
Holler up.
Can we raise the lights? Thank you.
Thank you. I still can't see anything. Any questions? Joe.
The K change, it has to do, the K change, what exactly are you measuring with the LMA during the K change? What part of the process is the
We're always measuring the VHF radiation. So basically, the K change starts out as what's called a recoil event in the positive breakdown region, and that is the same thing as a dart leader. If it was a cloud ground discharge, that would be a dart leader, which then goes to ground. But if it's occurring during an intercloud flash, it's a dart leader, which essentially goes upward in the cloud, but it's called a K change. And so it's just transferring more charge between the mid-level negative and upper positive charge of the storm. But it's doing that multiple times. In other words, you have just continual repeated events like that. And that's what the interferometer data shows in detail.
So is the picture there's a streamer zone around it which is sensitive to it?
Well, we're not sure exactly what the cause of the radiation is. It's due to stepping of the negative breakdown, basically. So the negative breakdown propagates, even though it's a dart-type leader, it doesn't propagate continuously. It has stepping to it. And so we're picking up the sources from that, basically, with the LMA. And with the interferometer, we can be picking up more continuous radiation events.
Time for one more question. If not, let's thank our speaker again. Our next talk will be the estimation of non-inductive ice-ice collisional charging by Jim Dye.
Thank you. Might as well start out. In the last few years, there's been evidence in several regions that we may have electrification occurring in some long-lived anvils in which it's unlikely that there's supercooled water present. And so today what I'm wanting to explore is the possibility that the non-inductive ice-ice collision process without supercooled water being present might be responsible for the charging that we're apparently seeing in this region. For that, I'm wanting to use an example from the Airborne Fuel Mill project, which conducted in Florida in 2001. I spoke about this particular case 4 or 5 years ago at AGU. The details, is the mouse working? Oh, there it is. Okay, thank you. The bright light, it makes it a little hard to see. So you can see details of this case in JGR in 2007. For the point of this talk, I want to point out that we're looking at CAPIs here over a 70-minute period. We followed the storm for almost 2 hours with the first pass very close to the anvil, 10 to 15 kilometers away. Excuse me. You can see the extension of the anvil with time. This is 50 minutes later, 20 minutes after the previous one. And we see that the aircraft's flying at high altitudes, 9 to 10 kilometers. The field remained strong throughout this whole period, and there was no liquid water that we observed in this cloud. I'm going to use these points here, A, B, and C. I'm going to show you size distributions at those points and use that then to calculate collision rates and also then to try to, based on laboratory results, make an estimate of the kind of charging we might expect.
So this is one of the size distributions from A, and this is diameter on a log scale from 100 microns up to 1 centimeter. And this is normalized concentration over many orders of magnitude. On the right, we have images from the 2D probe. This is a scale of 1 millimeter, and from the high volume particle sampler scale of 5 centimeters. So you see that the large particles are aggregates, small particles are perhaps frozen droplets, or irregularized particles. The main point of this slide is that we have a very broad ice distribution. We have particles of 100 microns or less that are very high concentration, and large aggregates of several millimeters up to a centimeter in the lower part of the cloud that are existing. This is at point B. It's very similar. See similar things. This is point C, just to show you the similarity. Now you could say that I tried to pick as similar as possible, but that's not in fact. I actually tried to pick the regions and turned out that they were similar. But that's one of the characteristics that we've seen in these anvils. Now on this slide, I've overlaid those three distributions. You can see they're virtually on top of each other. And I have this normalized concentration I'm showing here. So in order to compare one instrument with the other, we typically divide by standard unit of measure. But in order to get physical units, I've actually converted that so you get an idea of the number concentration we're talking about. So in 100 microns in size, for example, we're talking about 10 to the fifth per cubic meter, or 100 per liter. So that's a very high concentration. When you get out to 5 millimeter size, these large aggregates are 20 per cubic meter. So it's many, many fewer. I want to point out that there's very large measurement uncertainty with the instruments we have here, breakup on the probe tips, also some of the electronic optical characteristics. In this region, there might be errors of the factor of 5 or as much as 10. Whereas in this region, most of the, there's uncertainty, but it's probably well less than a factor of 2, I would say. Now, using those size distributions, I want to try to calculate the collision rate. And for this, I'm basically assuming that the larger particles falling through the smaller ones, and we compare the area of the large plus the small one, multiply that by a terminal velocity difference, and then look at the collision efficiency, and then, of course, the number of concentration of the particles in each of these phase ranges. So this is then particles of large size d colliding with the smaller particles of small d. If we want to look at the total collision rate, we need to sum over all particle sizes. I keep losing, there we go. But in terms of looking at the collision rate, the main uncertainties we have are the concentration of particles less than roughly 100 microns in size, which can be large, and also collision efficiency of the smaller particles with the larger ones. In terms of terminal velocity differences, we actually have very little difference, uncertainty, both from laboratory studies as well as studies of natural crystals. The main point here is that the terminal velocity difference between the large aggregates and the smaller 100 micron sized particles is 1.5 to 2 meters per second. So there's appreciable time for vertical separation, sufficient. Here, this looks at the collision rate as a function of size. The main point to take home from this is that those particles in the very small region are undergoing many, many more collisions than those in the large region. Now, this is looking at the total collision rate of these spectra over the 2-hour time period of the aircraft observations. And for this calculation, I've assumed 3 different things. I've looked at the spectrum with particles greater than 50 microns, greater than 100 microns, and greater than 200. And see, the collision rates are really quite high. That, for example, if I look at all the particles, we have several thousand per cubic meter per second. These are my spectra now, A, B, and C, and so you see that, in fact, some of the collision rates for A, B, and C are slightly less than some of the larger ones, but the collisions are very high. So then I'm using these collision rates and trying to estimate the total charge that might be happening, produced on the micro scale. And for that, I have to know what the charge per individual collision is. And that's where we really have major problems. So here I'm showing an equation for the total charge that we might produce on the micro scale in a volume of 20 by 20 by 3 kilometers vertical thickness. I'm assuming that this is going to take place over a 10-minute period, which in an anvil that lasts for 30, 40, an hour or more is a relatively small period of time. So these expectations of area and time are pretty small. The biggest question here is what is the charge per individual collision. Before I go to that, I just wanted to point out that based on terminal velocity differences of 1.5 to 2 meters per second between the small and large particles, in a 10-minute time period, we can get vertical separation of a kilometer. If we look at 20 or 30, we have vertical separation of 2 to 3 kilometers. So we shouldn't have problem of separating the charge on the larger scale. So turning now to the charge per collision, if you look in the literature, most of it is back in the 70s, 80s, and just a little bit in the 90s. And this is when the community was very actively trying to understand what was going on with the non-inductive mechanism, what's the source of the charging. So there's not a lot of literature on ice-ice collisions without supercooled water being present. This is one of the results from Keith and Saunders, 1990. In this case, they're looking at vapor-grown crystals colliding at 3 meters per second on a rhyming, well, they grew it through rhyming, but there's no water present there, at minus 15 C. And they looked at particles in size range of 200 to 500 microns in size. For the larger ones, 400 to 500 microns in size, the charge per collision they found was about 1 femtocoulomb for each individual collision. This is in the region in which sublimation was occurring, so it's negative charging. If we look at other results, earlier results from Gaskell and Illingworth, again in sublimation region, so negative charging, here they were impacting 100 micron frozen droplets on a target at various speeds. They looked at it at 6 to 12 meters per second. If we extrapolate the results backwards from here up to 1.5 to 2 meters per second, we see that the charge per collision here is about 3 femtocoulombs per collision. Now, these are smaller particles, but yet producing more charge than we found from Keith and Saunders. They also looked in less detail, but they also looked in a region in which they had deposition occurring on their target. They were able to cool the target. And in that case, the charge per collision was much, much larger. And since they were looking at individual collisions, there's a spread of charge per individual collision. But rather than a few femtocoulombs per collision in the region in which evaporation of the target is taking place, but growing by deposition, the median was 80 femtocoulombs collision. So there's a huge difference there. Then we step ahead to results from Caranti et al. And these were done somewhat similar to the results of Gaskell and Illingworth. They're looking at the collision of individual particles, frozen droplets of about 100 microns in size, impacting at 8 meters per second on their target. Again, they were able to cool the target. So they actually looked at the charge, the change in charge as they cooled this target. You see that in the region of sublimation that we have negative charge occurring, whereas as soon as we get into the region of deposition, there's an immediate change to positive charge. And notice that the charges are much larger. I keep losing the arrow. There we go. So here it's minus 30 femtocoulombs per collision, relatively independent of the subsaturation of the target. If we go into the region of deposition, then we have much, much more charge produced. Now these are with sub and supersaturation conditions of a couple of to a few degrees. So if we're really going to look in an anvil or in the stratiform region, we really need to be talking about sub and supersaturations in a much smaller region, of just a small fraction. I don't have time really to go into the charge, the sign of the charge transfer, although it's very interesting and controversial. Now, using the collision rates based on our observed particle size distributions and also using some of the laboratory works, I'm now looking at the total charge accumulated in this 20 by 20 by 3 kilometer volume in a 10-minute period. And this plot uses the results of Keith and Saunders in 1990, which I believe is the low end of things. Now, one of the parameters we also need to examine is what's the probability if a nice small crystal collides with this aggregate that it's actually going to separate and move charge rather than just aggregate and just remain part of the crystal. I've assumed that's 1 out of 10. 1 out of 10 will actually separate. It could be much smaller. But what we see here, making these assumptions, and the Keith and Saunders charge per collision, is that over the lifetime of the storm, as we're flying in the anvil, that we're producing something on the order of a few tens of coulombs in this time period. So up to perhaps a maximum of 100 coulombs. Just for comparison, I've also used formulation of Brooks et al. Now, this is what some of the modelers use for trying to look at electrification in their models in which rhyming is occurring. And rather than a few tens of coulombs per second, we have hundreds of coulombs occurring in the same volume. So I'm not sure I really have time to talk about this, but if we look at then the distribution, this is 2 hours of time of our flight, and this is diameter on this scale versus the charge, total charge generated. We see that most of the charge is on the largest particles of aggregates of 2 to 3 millers in size, and rather than on the very smallest particles, it's on 1, 2, 300 microns in size. So then, in summary, I can let you read that, but I want to conclude that the non-inductive ice-ice interactions without supercooled water present are probably capable of explaining slow rate charging in anvils and also in trailing stratiform. Of course, there are a number of uncertainties which I've spoken about, and you can read more here. Thank you.
Time for a quick question?
I'm wondering about the condition rates. I was recently talking to a number of people in turbulence, and they're actually say that typically particles are not equally distributed. There are certain parts where they strongly accumulate, and that would actually change your condition rates. Is this included in these numbers, or is it purely now for measurement?
If I understood the question, no, I mean, turbulence could impact the collision rates. I certainly agree. And I didn't understand, did you say that it could increase it or would it decrease it? Yeah, yeah. Well, that would add to this, obviously, and certainly these irregular particles and aggregates are falling in a very turbulent manner, as well as being in a turbulent environment. So that adds power to actually all of these mechanisms we're looking at, the non-inductive mechanism.
Just a comment, there is recently a very active community, at least in Europe, in this type of turbulence with tracer particles, but I don't know whether the contact between
Yeah. And I know that you're aware that there are work in the U.S. as well, but unfortunately, I think, as you're suggesting, there's not a lot of communication with the talks, and even, I mean, the basis of a lot of this is really the microphysics, and there's not as much communication between the microphysics. Some of the basic questions I'm asking here, the microphysics community really needs to answer. So.
Let's thank our speaker again. Our last talk will be a comparison between the in situ and remotely sensed storm microphysics and electrical characteristics by Andy Detweiler.
Well, we started with lightning, and we're ending up with microphysics and what leads up to the lightning. Let's see, just click the...
Yes, click the mouse in advance.
And I'm going to have to talk about less than I thought I would when I put in the abstract. What I really wanted to do is go back and take a look at what you can do with an LMA as far as diagnosing where charge is in a storm and the polarity of the different regions of the storms, which Paul Crable just went over. And this is much older data. This is from 2000, even older than Jim Dye's data. And the sources here are coded red where there's inferred positive charge and blue where there's inferred negative charge. And the question is, can we make in situ measurements to compare to this? And there have been historically a number of efforts to measure charge on particles in thunderstorms. The upper left is Professor Takahashi's video sonde, and he can launch that on a balloon and get a video image of particles as well as an indication of the charge. Lower left is some work that Monty Bateman did back in the 1990s, where he has induction rings inside of basically a beer can-sized sensor or instrument and a light beam that he can infer size by the amount of time it takes the particle to get through the beam. And the upper right is an older instrument from Marshall and Wynn, where they had induction rings, could measure charge, and they had to infer something about size from the speed with which the signal progressed from one ring to the other. On airplanes, there have been attempts to make this kind of measurement, and the upper left is basically a diagram of a PMS 2DC probe. You can see the arms sticking out here. They put a induction ring device between the probe arms, and so the particles go through. They're imaged up here in the laser beam that the probe was designed to have, and then you get a charge signal from induction rings inside this housing here. And Jim Dye did some work like this a little bit later with a similar device on the NOAA NCAR sailplane. And then the instrument I am going to talk about is a spec HVPS second generation probe that was modified by people at New Mexico Tech led by Bill Wynn, and they put some plates, segmented plates around the sample volume, and so the particle goes through the arms and gets imaged by an optical arrangement here and induces charge on several of these plates, and from the charge signals you can retrieve the particle charge. And one of the issues with this type of measurements is to match up the optical sample volume and the charge sample volume, and the HVPS arrangement achieves a pretty good balance. There's about 70% of the charge sample volume is actually imaged optically, so you get a pretty good match between imaged particles and charged particles in theory, but the problem is that the sample volume is too large, so that we found in typical storms we flew in, there were always multiple particles between the plates, and only one of them was imaged, and so it became a problem to analyze the data. The HVPS could detect particles down to 0.2 of a millimeter, and was sensitive down to a few picocoulombs. Previous experience by everybody who's tried to do this sort of measurement is that you can usually, you have very noisy data, you can only retrieve a good estimate of charge on a small fraction of the passing hydrometeors. There are sampling rate limitations. You can only, you have to wait for the particle to get past all of the induction rings or plates or whatever you have, and you can't calculate another charge while the previous particle is in there. And you get signal contamination from particles that are hitting the charge sensing surfaces. And generally, although people hope to automate the analysis, they've had to do things manually. And so if you look back historically, the one instrument that was on the NCAR NOAA sailplane made a quite dramatic flight up to a thunderstorm in New Mexico. Andy Weinheimer reduced the data. They detected almost 25,000 hydrometeors and during a 6-minute segment of flight when they were in the upper part of the updraft region, but could only retrieve the charge for 269 out of all of those images. And I think Andy probably had an assistant that did most of that work. Professor Takahashi's video sonde is limited electronically to sample only 2 particles per second, but he's sweeping out a volume of about 70 liters during that 2 seconds. So obviously there's a problem there too. You're not able to detect the charge in all the particles, just a small fraction. This work has shown, the prior work has shown, that typically there are charges of both signs present in most of the regions that are sampled, although occasionally, and in particular regions of storms, you find net charge of one sign or the other. And Bateman, in his work, hypothesized that when you're in a region of active charge separation, you should get a definite polarity, a net polarity in a region. And the other typical relationship for the probes that can determine both size and charge is that usually there is no correlation between size and charge, although from the collision-based mechanisms you might expect charge separation to large particles to have more charge and smaller particles less. So I want to take a look at some data from a flight that was made during the STEPS project that Paul mentioned. And here's again the characteristics of the probe. We were able to sample particles larger than 0.2 of a millimeter and charges down to a picocoulomb or so. And this probe produces image records that contain about 35 images apiece. And I was typically able to only analyze or determine a charge for maybe 1 out of those 35 particles on the average. And my problems typically were coincidence. You could tell from the signals on the charge plates that there was more than 1 charged particle in the sample volume. When particles collide with the plates, they dump a lot of charge on the plates, and it takes time for that charge to be bled off, and that corrupts your ability to detect new charges on passing particles. And it looked like in regions where there was liquid water, maybe above a couple of grams per cubic meter, our de-icing wasn't working as well as it should have, and we didn't get any signals. And it could be that there were no charged particles, but it could also be a problem with icing of the probe. And so we'll take a look at one thunderstorm in particular. This is the one that occurred on June 29th of 2000, which many people have studied and also simulated. And this is a radar history of the storm produced by Sarah Tessendorf. The storm, the scale here is plus 80 to minus 50 kilometers, and the timeline here is about 3.5 to 4 hours. And this is just a Hove-Muller diagram of the radar reflectivity. The X's are cloud to ground, positive cloud to ground, and the zeros are negative cloud to ground events. And if you look at some work that a student who was working with me, Heather Kay, did last year, the storm went through, this is an echo time height diagram, and you can see the echo fluctuating around as the storm intensifies, decays, intensifies, and decays. And the part of the storm we're going to look at occurred right in here as the storm was intensifying, and it was turning to the right here, becoming a true supercell, and there was a tornado coming out of the base at the time. So here is a CAPI at 6 kilometers of the radar reflectivity, and here's the path of our airplane going through the storm. Here's a trailing stratiform leading precipitation region. This was the storm was being fed from the southeast here, and the anvil was advecting off to the southeast, feeding from the southwest, advecting off to the southeast. This is a Doppler analysis that Sarah Tessendorf did showing strong updrafts up in this region and neutral to descending velocities in this region out here. Here is a vertical profile of the reflectivity along the aircraft track going from south to north, and in this high echo region here, most of the precip is above us. And so here is a map of the traditional LMA presentation, the XY plot, the east-west cross-section, the north-south vertical cross-section. And Kyle Wiens has he identified all of the strokes, events in the LMA data here and classified them as either positive or negative. So we have a central positive charge region with a lower negative and upper negative region. Oh, and I guess I can't go back. The airplane is flying along right at the lower boundary of the positive charge region. And I looked at two separate sections, roughly 100 buffers. It's about 3,500 particles. I was able to get charges on less than 100 in each of those periods. This is up near the updraft region, on the flank of the updraft where you have some growing hail. And this is in the downshear precipitation region. The scales are different. In this region, we're getting charges ranging between maybe plus 15 to 20 and minus 15 to 20 picocoulombs. In this region, we have a lot of charges in that region, and along with a few larger charges. And the net charge, if you compute it here to within the noise level, is 0. It's neutral. A second pass was made by the airplane across the downshear precipitation region from north to south. All the action is up here where the updraft is. Reflectivity is much reduced. And we're finding mainly similar structure. Here's the path of the airplane projected on the east-west plane. Here's the path going through the storm. Here's your lightning hole associated with the updraft. And you can see that the airplane is flying again along the lower part of the region identified as net positive charge using the LMA. And again, we find basically as many positive as negative particles. In the northern portion, we found, I was able to get a few more retrievals, but again, minus 50 to maybe plus 40 or 50 picocoulombs. This region is down on the southern end of the downshore precipitation region where there were some cells feeding in from the southwest. There was a little bit of liquid water, but still mostly lightly rhymed particles. So neither of these passes and the regions analyzed during the passes showed a consistent relationship between charge and particle size. If you use the laboratory results that Jim was talking about to infer what kind of charge separation should have been taking place given the temperatures and the liquid water contents, et cetera, in almost all of these regions, the larger particles, the grapple particles, should have been, or aggregates, should have been positive and the smaller splinters negative, although what we see is equal amounts roughly of both signs. So was most of the charge acquired before these particles got to where they were sampled, or perhaps was lightning redistributing charge in these regions of the storm? Unfortunately, with the configuration of the horizontal passes, we can't really use the electric field measurements. We had to infer a total charge based on divergence of the electric field. But what I think was going on was that if there was charge separation going on, it was probably going on in this orange region here, and we either couldn't get samples or didn't see enough of that orange region to see any region with a net sign of one polarity or the other. Most of what we saw was this weaker, where there was weak non-inductive charging, and other prior charging of the particles is perhaps responsible for the fact that we have equal numbers of each polarity. So in summary, I was a little discouraged by this attempt to work with this data, and we're working on getting another storm-penetrating airplane, and I'm hoping that some instrument builders can come up with new ways to go at this problem, which is fundamental to understanding how electrification occurs. Thank you.
Time for perhaps a question?
Time for lunch.
Time for lunch. Earl.
And you did have one case where you had a preference for positive charge on the part. It was a mix, but it was a definite tendency.
Well, in these analyses, if you just sum up all the charges, they come up pretty close to zero, to within what you might expect on one particle. So visually, it's deceptive, I think.
Let's thank our speaker one last time. This concludes AE 12A, and one more round of applause for all our speakers.